Okay, good evening, everyone. So let's get started. So we were looking at.
Good evening, sir.
Good evening. So let us begin. So we are looking at the general iterative methods yesterday, right? In the context of a solution of elliptic equation. So we are looking at elliptic equations, and within this we looked at how does any general iterative method behaves, right? We said essentially we want to solve for ax equal to b or ax equal to b or a phi equal to b. We said a is being now split into a1 minus a2, right? And then we want to split it such that it is a1, it is kind of easy to invert than inverting the A matrix, right? So that's what we said. And then essentially the iterative scheme is going to be A1x k plus 1 or n plus 1 equals A2xn plus b, right? In which case we're going to start with a guess value for x, and then we're going to get an improved solution for xn plus 1, right? That is the idea we said for the in general for an iterative method. Okay, so there are three different methods which we will learn in the general iterative method. The first one is the point Jacobi method. Okay, so what we have is that in the point Jacobi method, we're going to split A as A equal to, I can either write, okay, notwithstanding the plus and minus here, I can split the A matrix itself into D plus L plus U, okay? That means, okay, so that means we are splitting it into a diagonal matrix. D is going to be the matrix with only the diagonal entries. Okay, so D will be the matrix with only diagonal entries. And then L is going to be the matrix. It's a lower triangular matrix. With elements, essentially lower triangular matrix with elements taken from A, right? Taken from A, which are actually the lower triangular elements, okay? And then D is going to be an upper triangle, U is going to be an upper triangular matrix. Is going to be an upper triangular matrix, okay, with all these elements. So that means if I have, let us say, if I were to write my A matrix, A11, A12, all the way to A1n, A21, A22, all the way to A2n, and AN1, AN2, all the way to ANN. Okay, so in this, I just imagine that my number of degrees of freedom is n. Okay, so then we're going to split this into three matrices. The first one is going to be A11, 0, 0, 0, all zeros, 0, A22, 0 all the way, 0, 0, A33, all the way, and so on till ANN. Okay, everything else is this is your D matrix. Okay, plus the lower triangular matrix is going to be all zeros in the numerator, in the first row, and I said it's going to be A21, 0, 0, 0, 0 all the way. Then it's going to be A31, A31, A32, 0, 0, 0, and then similarly it's going to be AN1, AN2 all the way to ANN minus 1. Okay, so that is your lower triangular matrix. That is your L, and then plus the upper triangular matrix is going to be 0, A12, A13, all the way to A1n, 0, 0, A23, all the way to A2n, and all the way to AN minus 1, N minus 1, 0, 0, all these zeros. Okay, so that is how I have split it. Now, let us not confuse here that L and D are actually not splitting A into LU. Okay, so earlier we have looked at how to decompose the matrix A into LU decomposition. We are not referring to this notation here. Okay. So we are not referring to this notation. We are just simply separating out elements of A into whatever that falls along the diagonal, that is this thing, and then whatever that falls along the lower triangular into this thing, and then whatever that falls into the upper triangular. Okay, so essentially that is this thing. Okay, so that's how we are kind of splitting it. Now we are doing this essentially to get a matrix that is easy to invert. That means we want to form this A1 matrix which is easy to invert. Okay. Now you may think, okay, I mean, I said A equal to A1 minus A2, but we have written D plus L plus U. You can think of it like D minus of L plus U. Okay, so that means this is A1, this is A2. So in the point Jacobi method, we're going to split the A matrix into A1 and A2, and the A1 matrix is going to be simply the diagonal values of the A matrix. Okay, and the rest of the things are grouped into L plus U into the A2 matrix. Okay, so that is the easiest possible split. We say it is easiest possible, and because it is very easy to invert a diagonal matrix, right? Inverse of a diagonal matrix is simply a matrix with all the elements, with the diagonal elements being inverted. That means inverse of this is going to be simply 1 by A1 1 0 0 0 0 1 by A2 0 0 0 and so on, right? So essentially it is very easy to invert a diagonal matrix. So point Jacobi method is the simplest possible such decomposition. Okay, so now that means if we go back to the equation, we have written what did we write? Okay, so essentially we have written A x equals b. Okay, let me write in terms of phi. Okay, so we have basically A phi equals b is what we want to solve. So we want to write A as A1 minus A2 times phi equals b. And then when we write this thing, we say A1 times phi n plus 1 equals A2 phi n plus b. Okay, so we are starting with a guess value for phi n. And then with that guess value, we are improving the and we are getting the next value for phi n plus 1. Okay, and then we said here in this context of point Jacobi, A1 equals D. So this is D times phi of n plus 1 equals A2 is going to be A2 was basically minus of L plus U. Okay, so this is minus of L plus U. So this is minus of L plus U times phi n plus b. Okay, that means if I want to get the new value for phi n plus 1, that is going to be minus d inverse of L plus u times phi n plus d inverse times b. Okay, so this is what I have to solve. So once I am given a guess value for phi, I'm going to solve for this and then obtain the next value for phi n plus 1. Okay, so next value for all the values of phi, right? We said phi is basically over the entire grid points, right? That's what we're going to solve. So here we realize that all the phi values here are vectors. Okay, these are all vectors going from m minus 1 times n minus 1. Okay, I have kind of little bit mixed up here. I mean, I wrote here capital N, but we realize that here n in this, what I'm referring to is the total number of degrees of freedom. Okay, so this is the total degrees of freedom, which is nothing but m minus 1 times n minus 1. Okay, so that's what I have kind of referred to. Okay, so that is your point Jacobi method. Okay, that means yeah. So but then what we realize is that in the implementation we are not going to implement this way. We are not going to work with matrices. Okay, so in the implementation we do not use matrices. Okay, that is good, because that's going to make it very easy to understand. So how are we going to actually implement it? So for that, let me go back to the previous equation that we have developed. We said when we want to solve for del square phi equals f of xy, we said this equation came out to be phi of I plus 1j plus phi of I minus 1j plus phi of I j plus 1 plus phi of I j minus 1 minus 4 times phi ij equals del square fij, right? That's what we have written. That means if I were to rearrange this thing, I can write phi of ij That means I'm trying to solve for a grid point at ij. That is, let us say I'm going to solve for this ij. Okay, that is my I comma j. Then that is nothing but minus 1 by 4 of phi of I plus 1j plus phi of I minus 1j plus phi of ij minus 1 plus phi of I j minus 1, and then minus 1 by 4 del square Fij, right? So that's the, is it correct? Phi ij, 4 phi ij. Oh, it's going to be plus, right? This is going to be plus. This is going to be minus. Okay. So this is what I got. Okay. So plus 1 by 4 of this thing goes this side. This comes this side. Okay. Is this correct? If there is a mistake, let me know. And then this should be minus, right? Because this goes this way. Okay. So that means what we have is that this is the equation we're going to apply at each and every grid point, right? At each and every grid point, ij, 1, 1, 1, 2, and so on. So what does this mean? Of course, now because we are applying Jacobi method, I'm going to write this as n plus 1. Okay, that is n plus 1, and everything on the right hand side is at n. So these are all at time level n. Okay, and then minus del square Fij. Okay, so what does this mean? This is basically more like an explicit method because excuse me, because if I know what is the n values, what is the values of the previous time step, right? So values at nth time level are known. So we can simply substitute for all these things and calculate phi ij n plus 1. Okay. So what we also realize that phi I plus 1j, I minus 1j, ij plus 1, ij minus 1. These are nothing but the 4 neighbors of the grid, right? If this is the point, then we are talking about actually east, west, north, and south are these 3 points, right? This is I plus 1j, this is I minus 1j, this is ij plus 1, this is ij minus 1. Okay, so essentially we just have to average all the 4 values, take all these summation divided by 4, that means we're calculating average, and then subtract off that minus 1 by 4 del square Fij, for this equation, right? For del square F equals F for this equation, and then update this new value. That new value we update as phi ij n plus 1. Okay, then we are done with that point. Then we're going to go to the next point. That means we're going to come here, and for this point again, we identify the neighbors. Neighbors are east, west, north, and south, right? We do that, and then we update this value. Then we come here again, calculate 1, 2, 3, 4, and then do it, right? Basically, we have to do it point by point. That means you would have in the implementation 2 loops, one running over j, one running over I, and then you would have one outer loop which is going to update it for the time level, right? For the time level, you're going to store all these values and update them into a new array that you're going to call it as some new array or something like that, n plus 1 array. Okay, so that is how implementation is done. So implementation is very easy, right? It doesn't deal with actually matrices, but you see here what we have done. So you should be able to see the correspondence between this matrix formulation of the equation and the implementation equation that we have developed. You can see that phi n plus 1 equals minus d inverse times L plus u phi n, which is nothing but this minus d inverse is plus 1 by 4, right? Because in the matrix we had minus 4, 1, 1 like that. So this is going to be minus of minus is plus, and then d inverse will have 1 by 4. So that's what we have. And then all the neighboring values. So this is all at, L plus u, because we had 1, 1, 1, minus 4, 1. So all these ones when multiplied with the neighbors are giving you all the summation. And then, of course, the b times d inverse is also here, right? That is your right hand side. Okay, so that is about the point Jacobi method. But then, as we discussed yesterday, the convergence, of the point Jacobi method depends on the spectral radius of this quantity, right? This quantity is your A1 inverse A2, right? We said the spectral radius of A1 inverse A2 is going to decide whether this method is going to converge or not. So spectral radius of A1 inverse A2, that means the spectral radius equals spectral radius of D inverse times L plus U, right? So this spectral radius should be, that means the eigenvalues of this matrix should be less than 1. Okay, only then essentially only then the point Jacobi method We call it point Jacobi because we are essentially doing point by point, right? Grid point by grid point. Only then point Jacobi method converges. Okay, it appears for several set of matrices, this condition is true, including diagonally dominant matrices. Okay, diagonally dominant matrices. Okay, so if you have a diagonally dominant matrix, then it satisfies that the eigenvalues of D inverse times L plus U are less than 1, and essentially point Jacobi method converges. What are diagonally dominant matrices? Diagonally dominance means, I think we have seen this thing before. Diagonally dominance means that the modulus of AII, right, is greater than summation of all the Aij of all the points where j is not equal to I, but j is going from 1 to n, right? So essentially this should be valid for all I equals 1, 2, 3 all the way to n. Okay, so essentially if this is satisfied, that means when you take a matrix, the values in the diagonals, right? So values in the diagonals, these in an absolute sense, these must be greater than all the absolute sum of the absolute values in the all other columns. Okay, so then we can say that the matrix is diagonally dominant. Okay, or it satisfies Scarborough criteria. Okay, so so for these matrices, it is kind of point Jacobi method works. Okay, so any questions so far on the point Jacobi method? So to begin with, you're going to start with the guess value. So this phi n are the guess values. That means whatever is the guess that is given, and then you're going to take an average of that and then update the next values. And when are you going to stop? You're going to stop when this entire phi at n plus 1 minus phi n in some norm, right? This should be n in phi n in some norm should be less than some tolerance. Okay, that is basically your stopping criteria. Okay, that is your stopping criteria. You're going to stop at that point. Fine. Maybe it will be clear when we do some numerical problems, but if you have any questions, feel free to stop me. Okay, let's move on to the Gauss-Seidel method. So second method is the Gauss-Seidel method. Okay, so Gauss-Seidel method, don't be confused. We have seen earlier Gaussian elimination, that is a direct method. Gauss-Seidel method is an iterative method. Okay, so this is different. So the starting point for the Gauss-Seidel method is the Jacobi method, where we realize that essentially that because we are going in a we're essentially updating the values in a particular pattern, right? I mean, let us say if you're going to update the values in this pattern, like you start with I and this is your j direction. Let us say you update the points value, this ij here, then you go here, then you go here, like you finish this thing, then you go here and so on, right? So if you're going to update it in this way, in this fashion, then what we see is that when you want to calculate phi ij at particular ij at n plus 1, that means let's say we want to calculate phi ij at this value. We realize that essentially we have already calculated phi ij at n plus 1 time level for all these blue circle points, right? For the remaining points, I have not yet calculated. Let us the blue circle points are at n plus 1 time level, and the red cross values are at the nth time level, right? Using the nth time level values, we have calculated what is it for n plus 1 time level or n plus 1 iteration. Now what we see is that means, but the point Jacobi method doesn't make use of the already updated value of phi at the neighboring points. For example, this when you want to calculate it for this point, we realize that point Jacobi method still makes use of these red cross values instead of the blue values that are available at these 2 points, right? That means if you're doing ij, the I minus 1 j at nth level and ij minus 1, that means this value and this value have already been updated, right? So these were already updated because only after updating them you have come to update ij. Okay, But then, unfortunately, point Jacobi method doesn't make use of the latest values. It makes use of the old values which are still there. As a result, the convergence of the point Jacobi method is a little slower. Okay, it's actually half than the Gauss-Seidel method. So what Gauss-Seidel method proposes is that because you have the values of phi minus 1j and phi j minus 1 being updated in n+1 iteration itself, right? So it makes sense to use the updated values of phi minus 1j and ij minus 1. That means use them at n+1 time level instead of at nth time level. Okay. So that is the modification that the Gauss-Seidel method does. That means if I were to rewrite this thing, so this is equal to 1/4. Let me write it here. So the Gauss-Seidel method says that use updated values of phi I minus 1j and phi j minus 1 that are available in the current iteration itself. Okay, so that means phi ij at n+1 is going to be 1/4 of phi I minus 1j at n+1 plus phi I plus 1j at n, because this is not yet updated, plus phi I j minus 1 at n+1, this is already updated, plus phi I j plus 1, this is to the top above us, this is still available as the old value, minus 1/4 del square Fij. Okay. So use these updated values. So that means now you can see there is a difference when we want to calculate this. We're using n+1 for the left and the bottom, and then we are using n and n for the right and the top. Okay, because they are not yet updated. So this is basically is going to be the equation for running the Gauss-Seidel method. Okay, but then how does it relate to in terms of A1 minus A2? Right. So like the theoretical framework that we have developed. So so that means we said A equals D plus L plus U, or we want to refer to it as D minus L plus U. That means this is A1, this is A2, right? This is my A2. So in the Gauss-Seidel method, what we say is that A1, so we will not write it like this. Okay, so this was point Jacobi. So we say that in the Gauss-Seidel method, we're going to use both D plus L as A1 and then minus U. So this is going to be my A1, this is going to be my A2, right? So that means, as you can see, it is not only the D matrix that is inverted here or taken to be at the left hand side, that which is going to multiply with phi n plus 1. It is the L matrix which is multiplying with I minus 1 and ij minus 1, right? These two entries are controlled by the lower triangular elements of the matrix, right? So that means you're going to use D plus L on the left hand side, which is multiplying phi n plus 1, which is going to give you these things, and then U, which is the right and the top, are going to be still left out on the right hand side. Okay, that means our equation is going to be D plus L times phi n plus 1 equals this is minus U phi n plus B. Okay, then my equation is phi n plus 1 equals minus D plus L inverse times U times phi n, and then I have plus D plus L inverse times B. Okay, so that is the matrix representation of the Gauss-Seidel method. Okay, but we know that we are not going to work it this way, right? This is only a matrix representation. So that means we are never going to use the matrices in implementation, and we are never going to calculate these inverses, right? So although here I have written as D plus L inverse times U times phi n, we realize that we are actually going to work out this one as L times, we're going to work it out as L times phi n plus 1, right? Times D times phi n plus 1 equals minus U times phi n plus B. So the way we're going to implement it is only phi n plus 1 equals, okay. So I have written this thing, but this is not quite accurate, okay, because we are not going to actually apply it like this. Okay, let me rewrite it here. So phi n plus 1 equals minus d inverse times L of phi n plus 1, and then minus d inverse u times phi n plus b. Right? So this is the correct way. Okay, so this is the correct way. But then I have only written this to show that the spectral radius is going to be the eigenvalues of d plus L inverse times u matrix. Okay, so spectral value of this thing should be less than or equal to 1, should be less than 1 for this to kind of converge. Okay, so we can contrast this d plus L inverse times u with d inverse times L plus u that we have for the point Jacobi method. Okay, so it is kind of different from there. Okay, but this is only the theoretical construct in terms of how splitting this matrix into A1 minus A2 helps us in calculating, in easily inverting it. Okay, but then the implementation is actually on this one. Okay, using this this particular expression. All right. So, any questions so far? So. So this actually, the Gauss-Seidel method was accidentally discovered like long time back before the advent of computers. People used humans as calculators. So humans were paid, people were paid some amount to do calculations. And then, and then what they found was they were actually getting faster solution if they had used the updated values rather than the old values. That's how they kind of, figured out. And that's how this method actually has came into existence. Now, one thing we note here is that the Gauss-Seidel method is GS is almost twice as fast as the Jacobi method. Okay, that means it requires almost half of the number of iterations used by the Jacobi method. Okay, so if Jacobi method is going to use 1000 iterations, Gauss-Seidel method for the same tolerance is going to just use 500 iterations, and it's going to converge. Okay, so that's why wherever possible we should use Gauss-Seidel method instead of the Jacobi method. All right, so there is one more variant that is called the successive over relaxation method. Let me put it here. So this is called the Gauss-Seidel successive over relaxation method. Okay, which is referred to as the GSSOR. This is a slight modification of the Gauss-Seidel method. This is the kind of the most successful iterative method. Okay, so what it actually tries to do is it tries to reduce the maximum eigenvalue of A1 inverse A2 matrix. Okay, so that is what it actually tries to do, but it doesn't appear so. But what it tries to do is that it will try to reduce the largest eigenvalue, because when you reduce the largest eigenvalue, convergence basically increases. Okay, fine. So what does this method do? So what this method does is, let us say we have, I define some vector d. Okay, and these are all vectors. Okay, d bar equals phi bar n plus 1 minus phi bar n. Okay, I'm not writing just bars here, but we realize that these are all vectors. Okay, that means this is going to be equal to d equals phi n plus 1 minus phi n. We realize that these are all vector quantities. Okay, so what is this d? This basically d is the difference in the solution between phi n plus 1 and phi n. That means difference in solution between current time step and the next time step. Okay, or next time step and the current time step. So, or the previous time step. So that is your d. So what we're going to say is that the the successive over relaxation method is going to change. It's going to say that when we want to calculate phi n plus 1 from phi n, we can write phi n plus 1 equals phi n plus d. Okay, but then it's going to say that this difference, whatever is there, it's going to say that I'm going to do an over correction, right? That means it's going to say add phi n plus 1 times omega times d. Okay, that means whatever is the correction you're going to obtain, you make an over correction. Okay, how does that help? Essentially, what we say is that okay, so we say we want to use Gauss-Seidel method and calculate what is phi. Okay, so we calculate phi of ij at n plus 1. We call this as n plus 1 tilde. Okay, that's going to be 1 by j of phi I plus 1j at n plus phi I minus 1j at n plus 1. I mean, pay attention here. Whenever I use I minus 1, I'm using n plus 1. Whenever I use I plus 1, I'm using n. This is because of the Gauss-Seidel method, because those values are already available at the current step. Similarly, phi I j plus 1 at n, and then phi I j minus 1 at n minus 1 by 4 del square Fij. Okay, so that's what I have. So this is what you got from the Gauss-Seidel method. But then we say that this is not the final value. So successive over relaxation says that this is not the final value to be used. Rather, calculate the difference. The difference is basically now phi tilde n plus 1 minus phi n. Now you calculate the final value, which is phi n plus 1 equals phi n plus omega times d. Okay, that means this is phi n plus omega times phi tilde n plus 1 minus phi n. Okay, so that is my phi n plus 1. Okay, so that is the formula. Fine. That means you're going to take the previous value and you're going to calculate this from the Gauss-Seidel, and you take difference of that at that grid location, multiply it with some omega. Now this omega is the relaxation factor or the over relaxation factor, which actually can be optimized, but we are not looking at that part, which can be optimized, and typically it can be taken to be, it is usually more than 1. Okay, usually more than 1. Typically it will be somewhere from, the optimized values will be somewhere from 1.7 to 1.9. Okay, but depending on the problem, omega can be just greater than 1. That means values of 1.1, 1.2 are also used. Okay, so so that means what we're saying is that if this is the correction that we are supposed to make, you correct it more. You make an over correction to the previous value, and that is your new value for phi n plus 1. Okay, and this was also found kind of accidentally, and this actually gives, this will make the method converge much faster. Of course, in the absence of non-linearities and other things, this will actually make it, you know, probably almost an order of magnitude smaller than the number of iterations taken by the Gauss-Seidel. If Gauss-Seidel takes, let us say, some 300 iterations, the SOR method would only take around, you know, an order of magnitude smaller, probably around 50 or something like that. Okay, so that is the power of the successive over relaxation method, which reduces the number of iterations. Okay, any questions so far? How we work with point Jacobi, Gauss-Seidel, or the successive over relaxation methods? Okay, if no questions, let me try to solve a small problem here. So with either with point Jacobi, and identify and tell you how it will change if we were to solve with Gauss-Seidel. Okay, so we are given a matrix that is 3, minus 1, 0, 0, minus 2, 6, minus 1, 0, 0, minus 2, 6, minus 1, 0, 0, minus 2, 7. Okay, so that is the matrix we are given, and then we are given the value says phi 1, phi 2, phi 3, and phi 4 equal to, on the right hand side we are given 3, 4, 5, and minus 3. Okay, so for applying any of these iterative methods, of course we should be given what is the initial guess, should be given, If it is not given, you should ask what is the initial guess. So let us say we start with an initial guess of phi 0 equal to 0, 0, 0, 0. Okay, phi 0 bar equals 0, 0, 0, 0. That means all the four values are equal to 0. Okay, how do I do point Jacobi in this case? Okay, before I do that, let me just tell one more thing. What we realize is that in the point Jacobi method, because it uses old values, only the n values, we need to maintain two separate storage, right? That means we need to maintain two arrays, phi array at n, and then we need to maintain phi n plus 1 array, because it needs to refer to the nth values until all the n plus 1 values are computed. So as a result, Jacobi, not only it is slow, it is also going to be more memory intensive, right? Because it requires double the memory than Gauss-Seidel. Whereas in Gauss-Seidel, we can get away with just one array, phi n plus 1 or phi n, whatever, which can, because we can all update the value as soon as we get this value. Of course, you may say that, okay, what about calculating the error? For error calculations, we still need to have another array, but then that can be done cleverly without actually allocating an array. That is also possible. Okay, if you are going to do it element by element, we don't need to allocate an array. Okay, but then as far as the methodology is concerned, you don't need another array for Gauss-Seidel. You can override the existing values, right? Because as soon as you have updated, you can override them, and then that value will be automatically used when you go to the next grid point. Okay, so that's what I wanted to say in the context of this point Jacobian Gauss-Seidel implementations. Okay. Now let's look at this problem. So how do I, so first of all, I have to reduce this problem into a set of equations. So what we have is 3 times phi 1 minus phi 2 equals 3. Okay, and then I have minus 2 times phi 1 plus 6 times phi 2 minus phi 3 equals 4. And then we have minus 2 phi 2 plus 6 times phi 3 minus phi 4 equals 5. And then minus 2 phi 3 plus 7 times phi 4 equals minus 3. Okay, so this is what I have. So if I were to apply Jacobi method, I think you will see the clear distinction now between Jacobi and the Gauss-Seidel. So Jacobi method, because we are starting off with this initial condition as 0, 0, 0, 0, my phi 1, I want to calculate phi 1. So phi 1 equals 3 plus phi 2 divided by 3, right? That is the equation. So we're going to put phi 2 equal to 0. So this is going to give me value of 1. So this is phi 1 of 1 is this thing. Okay, then I want to calculate what is phi 2. Phi 2 equals 1 by 6 of this equation. That is 4 plus 2 phi 1 plus phi 3. Okay, now see here, I'm going to use 4. For phi 3, I'm going to use 0. So that's going to be 4 plus 0 plus 2 phi 1. I'm still going to use 0 here, right? Although I have just calculated what is the new value for phi 1, I'm still going to use 0 for this thing because this is point Jacobi, right? I'm going to use only the nth values here, not the n plus 1th iteration value. So this is going to be 0, 0. And then this is 1/6 of this thing. This is going to be 2 by 3. Similarly, phi 3 is going to be 1 upon 6 of 5 plus 2 phi 2 plus phi 4. That's going to be 1/6 of 5 plus. Now you can see phi 2 and phi 4. Phi 2 I have already obtained as 2 by 3, but I'm still not going to use it because it is point Jacobi. I'm going to just use point 0 and then 0, which are the initial values. Okay, so this is going to give me 5 by 6. Similarly, phi 4 is going to be 2 times phi 3 minus 3 divided by 7. So phi 3, although the new value is there, I'm not going to use it. So it's going to be 0. That means this is going to be minus 3 by 7. Okay, so that is the first iteration values for phi 1 to phi 4 that we have obtained with point Jacobi. Of course, if you ask you, we have to probably do second iteration, then you can do the same thing. The equations are the same. So calculate phi 1 at the second iteration. So that is phi 1 at second iteration is going to be 3 times phi 2 at first iteration divided by 3. Okay, you're going to get that. Then phi 2 at second iteration is going to be 1/6 of 4 times 2 phi 1 plus phi 3 1. Okay, you want to do that. Again, you realize that phi 1 1 is what you're using here, not phi 1 2. Okay, and so on. So that is how you can perform the iterations. If you, let us say, if I ask you to do 3 iterations or 4 iterations, you can do like this. Fine. So that is the idea. Now, how does it differ if you were to do the Gauss-Seidel method, then what we're going to do is, let me copy paste this one because, okay. Okay, so if I'm going to do Gauss-Seidel, okay, so then what should I do? Then my P1 will not change. P1 is going to be the same. So this is 3 plus Phi2 divided by 3. Phi2 equals initial value is 0. So this is going to be 1, right? So this is 1 just like before. And then P2 is going to be 1 by 6th of 4 plus 2 Phi1 plus Phi3, where we're going to use P1 as the 1 value, right? And Phi3 as the 0 value. Okay, so that's going to give me 4 plus 1, that is 5, plus 0, that is going to give me 5 by 6, right? Earlier you got only 2 by 3. Did I do it correctly? 4 plus, yeah, correct. So that is correct. Then Phi3 is going to give me 1 upon 6th of 5 plus 2 Phi2 plus Phi4. Again, to Phi2, we're going to use the 1 value. Okay, and then Phi4, we're going to use the 0 value because that is not yet computed. So that's going to give me 5 plus 5 by 6 upon 6. So that is going to be 35 upon 6. So this is going to be 35 upon 36, right? Similarly, Phi4 at 1 is going to be 1 by 7 of 2 Phi3 at 1 minus 3. Okay, so earlier this has come out to be minus 3 by 7. Now, because Phi3 of 1 is 35 by 36, we're going to basically get some 70 by 36. So that is 70 minus 108 divided by 36 into 7. So we're going to get some value. Okay, so that is how you would do if it were the Gauss-Seidel method. Okay, and this is how you would do if it was Jacobi. Fine. If it is going to be the Gauss-Seidel SOR, of course, we will not try to do it with hand, but when you code it up, you can simply say, once you calculate this one, you can say that my new Phi1 of 1 is going to be your Phi1 of 0 plus whatever the relaxation factor that is given to you times the Phi1 of 1, the tilde that is calculated using the Gauss-Seidel. Okay, so that is how you would do it for all these 3 methods. Okay, any questions so far?
Sir, just a question on Gauss-Seidel method, this Phi2.
Yeah.
We have given 1 by 6 into 4 plus 2 Phi1, right? Phi1 is 1 only.
4 plus 2 Phi1, yeah, and then, yeah, Phi1 is 1.
Okay, so it Phi3 is already 0.
Phi3 is 0 because we have not yet updated, because you know, if you are calculating this thing, whatever is previously we have calculated, we can make use of.
Okay, so then 6 by 6 is also 1, right?
Oh, did I make a mistake? Oh, sorry. This is 6 by 6, not 5 by 6. Yeah, 6 by 6, this is 1. Yeah, you are right. Okay, I thought this was 1. Yeah, this is 2 times 1. So this is 6 by 6, this is 1. Then it will change here. Then this is going to be 2 plus 5, 7, 7 by 6 instead of 35 by 36, right? Yeah, this is going to be 7 by 6. But you see that the solution is already different. We got 1, 1, 7 by 6, but here it came out to be 1, 2 by 3, 5 by 6 something. Okay, then this will also change. Okay, so because we're going to use 2 times Phi3 at 1, this will be 7 by 6 minus 3. It will be some minus value. Okay. Oh, no, not minus. It still be 14 by minus 18, minus 4 by 7 or something you will get. Fine, this is correct. Yeah, thank you for correcting. Is it okay?
Yes, sir.
Yeah, and the numbers could be incorrect, but what you should see is that we are using the updated value whenever we want to do it. For example, this is already updated here, so we make use of that. Here, this is already updated, we make use of that. Here, this is already updated, we make use of that. Okay, any other questions? Is it okay? The method is clear?
When this iteration will stop?
Sorry, say it again.
When this iteration will stop?
No, your voice is not clear to me.
Can you hear me now, sir?
No, there is a lot of background noise.
Can you hear me?
Maybe his question is when we should stop the iteration.
Oh,
sir.
when we should stop the iteration? No, you stop the iterations when, let us say, as I said before, your phi n plus 1 minus phi n in some norm is less than the given tolerance. That means you look at all these values. If all these four values are not changing from iteration to iteration, or they are changing less than this tolerance in some norm, then you can stop it. That means you are essentially leading to some converged values. Okay. So some norm, infinite norm, 2 norm, something like that. Other questions? No, is it clear? Okay, so this methodologies are clear. Okay, so coming to the, so I'll go to a different class of methods now, but before that I just want to say something. So tomorrow I won't be able to take a class because I have another MTech Viva that I have to attend. But what about Friday? Are you guys free on Friday?
This Friday, sir?
Yeah.
This Friday, okay, sir, same review only. We can take it, sir, not a problem.
Is it okay? Will everybody, most of you will
Yes,
be able to
sir.
join?
Okay, sir.
Yes, sir. Yeah.
Okay, so we will see. Maybe we'll take one on Friday, then we may take 3 classes next week.
Okay.
That should be okay. Otherwise, we can do 4 classes next week also. That is also fine, depending on how we make progress.
Okay.
I think it's better to take one this Friday so that we can make some progress, so that syllabus will be completed a little early, maybe. Right?
Sir, this week is better, sir.
This week is better. Okay, so let's try to meet on Friday because tomorrow I can't join. I have a MTech Viva at 3:30 that will go all the way to 4:30. I think it will be delayed. We can meet 4 o'clock is fine, no, on Friday, or should we do it? I think earlier would be difficult for you because you will be in your, job.
4 o'clock is better, sir.
4 o'clock is fine. Yeah. So I'll inform the code office to meet on, arrange a meeting for us on Friday at 4 o'clock. Okay.
Right.
So we'll do that and then we'll see either we take 3 lectures next week or 4, depending on that. Fine. Okay. Okay, good. So, yeah, so these are the general iterative methods we have seen. Of course, there are other iterative methods also. There is another method called multi-grid method, which we are not learning, but which is also very popular because if you take most of the CFD solvers, they use multi-grid method, which is a variant of, the Gauss-Seidel method that we have learned. So it's going to work with different mesh resolutions in order to quickly damp the errors. Okay, to quickly damp these errors, but we are not looking at that. That's going to consume 1 or 2 classes or something. Anyway, it's not there in the syllabus. But then we would like to look at another class of methods which are known as the known as the gradient methods. These are known as the gradient methods, or also known as the global iterative methods. Okay, what these try to do is that they kind of reformulate the problem. Okay, that means we want to solve A phi equal to B. Okay, so this is what we want to solve. They reformulate the problem such that instead of solving for A phi equal to B, they say that we will solve something else. That is something related to this one. What is that something else? Is essentially they reformulate the problem as a minimization problem. Okay. That means you know that if I have some function, I can always try to minimize that function. So they're going to build a function and say that if I can find the minimum of this function, that is same as solving for A phi equal to B. That means phi, which happens to be the minimum of certain function, which we're going to see soon, is also going to be the solution for A phi equal to B. So that is the idea in the gradient methods. Now, you know, from optimization, we can do minimization of a particular, you know, objective function and things like that. So this function, this function that gradient methods actually use is as follows. But before that, I want to make sure that, I mean, what we're dealing with is A is a matrix. If I were to write, I can write double arrows here, double, you know, lines here. Phi is a vector, B is a vector. Okay, so but we already know that this is a vector, this is a matrix, and this is a vector. So I'm not using this notation of bars on the top because it's going to make it very complicated to understand. But we know at the back of our mind, whatever I'm writing here in this chapter, especially in the context of gradient methods, these are actually vectors or matrices. Okay, if it is a scalar, I'm going to explicitly say that that's a particular thing is a scalar. So they're going to construct something that is known as Q as a function of phi. Okay. Which is equal to half of phi transpose A phi minus B transpose phi plus C. Okay, so this is what the method basically constructs. But we know that each of them is actually a vector. So this phi is a vector, Q is a vector, phi, this is a matrix, is a vector, 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 and C is also a vector of scalar values, right? So this is also a vector of scalar values. Okay, so is a vector of scalar. So this is the function we are kind of built, and the minimum value of Q of phi is going to be the solution to A phi equal to B. Okay, so because this function also contains A and B in here, so the minimum value, if you can find the minimum value of this thing, that is going to be the solution phi, which also will be solution to A phi equal to B. Okay, so that is the idea of the gradient methods. Fine. So we will not, I mean, we don't have time right now to look up on this thing. So we're going to begin this in the next lecture and then look at least one method. So there are a couple of methods. One is known as the steepest descent method. Okay. The other one is known as the conjugate gradient method. These are very popular. At least we will see if we can look at steepest descent method. If not, at conjugate gradient, depending on the time, we'll see. So I'll pick it up on in the Friday's lecture. Okay.
Professor, sir, can I ask a question if you allow?
Yeah, sure. Yeah.
So this is regarding assignment. I'm sorry to like.
Yeah, no problem. Yeah.
So basically, the first question that you have asked, sir, actually, y dash is equal to y, fy. Okay.
Yeah.
So so basically, what we have tried is that we have tried to expand it Taylor series of that and similarly coefficient that we have given also Taylor series, and then matching the coefficients actually.
Correct. Perfect. Yes.
Yes, sir. That's the way we are proceeding. So
Correct.
One thing, sir. Sir, I'm sorry to ask this very silly question, but can you just सर जस्ट एक बार बता सकते हैं कि वो जो कॉन्फ़िगरेशन है y डैश इज इक्वल टू fy, तो उसका अगर मैं टेलर सीरीज निकालने का प्रयास करूं, सो हाउ इट विल बी लाइक, आई एम सॉरी सर, दिस मतलब
no Taylor series of y prime equal to f of y, yeah
exactly sir.
No, you don't need a Taylor series of y prime equal to f of y, right? Oh, you would need it because you want to compare.
So y n plus 1 I plus 1 is equal to y into, like, because it's a derivative in this, so it will come fy dash and fy both will come in the picture, if I'm not wrong, right, sir?
Correct. Yeah. So what you're going to do is that, so this we have done in the class, no?
We have done in the class, but I've gone through the video. I just like could not grasp the complete concept, so I just wanted to.
Right. Let me see what we have done. If I'm correct. So what we're saying is that y prime equals, in this case, okay. So we don't even write. So equals f of y is what is given. Okay, and then you're given yi plus 1 equals yi plus some omega 1 k1 1 K1 plus omega 2 K2, right? That's what is given here.
Right.
So what did we do? I think in the class, what we have done is we have K1, K0, K2, right? K0, K1, K2, these are given. And then K1 is fine. Okay, so this is K1. The first one is actually K1. Second one is K0. So this is fine. This is H of F of Yi, right? So this
Yeah,
is not a
yeah.
problem. Yeah. But the other one is actually F of H
So
times F of Yi
that is
plus
very clear,
these.
sir. K1, K1,
Ah.
K0, and K2 expansion is very easy. There is
These
no issue.
expansion is okay.
Very easy. Sir.
Then
The
you can
point is
put it in
that-
here. Okay.
So that is clear, sir. Only thing is that yi plus 1, suppose, if I want to write
So
it,
Yi plus 1. So Yi plus 1 is going to be Yi plus
plus
H times Yi prime plus
exactly.
H square by 2 factorial Yi double prime
Yeah.
plus H cube by 3 factorial Yi triple prime.
Yeah, that is also fine, sir. Now here
Right.
the yi double prime, sir. So
Correct,
basically here the y dash is also involved, like function of function is there, sir, if I'm not wrong.
Correct.
So like I got little stuck in that area actually.
Correct.
So-
But then I think this will be much easier than what I have done in the class, because here you don't have a dependency on F of Y comma T. Okay. So it is only F of Y, not F of Y comma T. So you will not have that problem actually. So Y prime is directly equal to F of Yi, right? This is already there because that is what is given.
Yeah.
And then Yi double prime is going to be simply d by dt. Here prime is with respect to t, is it? Like I think some variable, okay?
Yeah.
d by
X.
dt of y prime, which is f of y,
Exactly.
right? So
Exactly.
what we said was this is d by dy of f of y times dy by dt, right?
Right.
So d by dy of f of y is going to be simply f prime of y, right?
Okay, so we have to apply chain rule, right, sir?
Yeah, and chain rule, and then this is going to be dy by dt is simply f of y.
Okay, sir. Fine. Sir.
This is much easier than what we have done in the class. In the class, we have got, instead of f of y, we got
xt.
I think we got similar. Yeah, this is basically the same thing. In the class also we have done this thing.
Yeah,
right?
exactly.
So we got f of y times f prime y. So this we got as f times f prime. Yeah, it will be the same.
Noted, sir. Basically, this first step that you have done, sir, that was skipped in the class, so I got just little stuck over there. So it's very clear to me. Clear to me.
Yeah. That's all. Chain rule only. Yeah.
Okay. So to just match the coefficients and calculate the value of y1, y2, or k0, k1, something like that. Right?
Yeah. Calculate the values of k1, k2, those things. Very
Sure.
this thing. Yeah. So calculate the values of omega 1, omega 2, beta 0, beta 1.
So thank you so much, sir. Thank you so much.
Yeah, no problem. Yeah. The second one is also straightforward. Second one, you have to use that Jacobian matrix that we have discussed in the class.
Right.
Yeah. We have not done an example, but you will be able to do it very straightforward.
Sure, sir.
Yeah. Okay. Any other questions, anybody? Okay, if no questions, I'll stop here. I'll see you guys on Friday. We will discuss steepest steepest descent method, and then see how it goes. It's going to be a little bit involved, but I think you will get the hang of it. I know that's a slightly different concept. Yeah, we'll do that on Friday. Okay. Thank you, guys. I'll see you on Friday.
Yeah, thank you, sir.
Thank you.
Thank you so much, sir.
Thank you very much. Yeah, bye.
Thank you,
Thank you,
sir.
sir. Thank you, sir.
Thank you.
Thank you, sir.
Thank you.